Oh, good afternoon. Today we're going to be discussing logarithms, and it's going to turn out logarithms are basically just exponents. And I want to
Fancy way of saying an
exponent.
A
Yeah,
logarithm is
an exponent. But some stuff we did the last time that might be important today, and it will be. Remember, we defined a zero exponent. Anything raised to the 0 power is 1, except for 0 to the 0 power. You can't hear me? Oh. Can y'all hear me? Do I need to put on the microphone? Is it still recording? Yes, it is. So, another thing we did the last time, we defined a negative exponent and how to work with a negative exponent if it's a fraction raised to a negative power. And something that I'm going to hope that you remember that we're going to be doing a lot is if you have something like 1 over, how do you write it without that 1 over? Well, you make the exponent negative. So this is just stuff from the last time. Like 1 over k to the 9th, to write it with just a k and not a 1 over, you make that exponent negative. We also defined fractional exponents. We had done those when we were solving square root equations. A 1/2 exponent is a square root, a 1/3 is a cube root, and so forth. We also said that if you have an exponent that's not just 1 over, then the bottom number is the root
on the radical,
and the top number is the power. So you take the 4th root and then cube it. That's the stuff that you're going to need to be able to do from that previous assignment over exponential functions. Something that I'll sort of expect you to know how to do is if you have a square root symbol, how do you write it without the square root symbol and just put an exponent? Well, a square root is a 1/2 exponent. A cube root would be a 1/3. A 4th root would be a 1/4 exponent.
Add that to your bag of tricks. When you run into radicals as we're expanding and condensing logarithms, you've got to convert them to exponents.
So today, I'm going to define logarithm, but first of all, that's a B I just wrote, not a 6.
B for base.
Yeah, I was going to say, if you see a lowercase b being used, it's the base. And let's assume it's always positive, and it's not the number 1. And why am I saying and not the number 1? Well, thinking in terms of exponents, 1 to any power is always what?
1 to the millionth. 1 times 1 times 1 times 1 a million times is still going to be what? 1. That's why we don't bother with a base of 1, because 1 to anything is still 1.
So here's our formal definition of logarithm. Log base b, that's a subscript. That's the first time. y2 minus y1 over x2, we use subscripts.
So they'd have to type them.
Yeah.
They're going to have to type the subscripts.
Log base b of x equals some number y means b to the y power is x. These two are the same thing. This statement here is the same as this. The only difference with an exponent, the base is written large and the exponent is the thing you write small. When you write that statement as a logarithm, the base is the thing that's written small, and the exponent is what is written a normal size. Y'all see what I mean by about large and small? Normally when you write an exponent, you write it smaller. Logarithms equal exponents. For instance,
okay, base, move your hand. Base to the power on the other side equals this thing that follows the logarithm. The thing that follows the logarithm is called the argument. Some books call it the parameter, but I think they quit that 30 years ago. So base to the power on the other side equals the argument. Look at this logarithm. If you understand the definition, you can tell us the value of this logarithm. 5 to what power? What exponent do you put on 5 to give 25? And don't say 5. 5 squared. 5, this number here is 2. 5 to the second power is equal to 25.
See, here's two ways. Most of you, I'm guessing, this is how you've seen it written before. 5 squared equals 25. And you're not shocked by it. Here's just another way of writing the exact same thing with logarithms. Logarithms, exponents.
Now, all the logarithms are going to be typed, and you're going to have subscripts you have to type. There are two special logarithms that don't require subscripts. And back before modern equation editors, those two special logarithms are the ones that most books, pretty much all you'd ever see, because think back to the olden days. It used to be a hassle to
Tim,
type
they don't
those
remember the
subscripts.
olden days.
Oh, goodness. People call them the good old days. I don't know what, I mean.
I think the people that call them good old days were just young back then.
And so that's why it was good to them, because they were younger.
Here's two special logarithms. Log base 10, if you have a little 10 there, it's abbreviated or denoted just log.
That's called the common logarithm, because for decades that was the most common logarithm used. Without a calculator, and without a calculator, it's hard taking numbers to powers. 10 squared, 10 to the 5th, you just count the zeros. And so that was the most common logarithm used in books and calculations. That's the first special logarithm that doesn't require a subscript. But if you type or write log and you don't put a subscript there, it's assumed to be 10. Okay?
The other one, I'm going to use a capital letter, although you should never type capital letters on Pearson.
Use a cursive L the way you did there.
But I'm doing both.
Oh, okay.
This is LN. When I write it cursive, it'll look like that. And I don't write a lot of cursive, but you'll notice my L's I'm writing cursive. Why is that? I don't want it to look like a capital I. Okay?
Or 1.
Or 1, but generally on the assignments, you'll get half the class emailing you, sending screenshots. Look, it counted it wrong. You've typed a capital I, E-Y-E, and not a lowercase l, E-L. Okay? So, this logarithm, is log base 2.718281828. That lowercase letter e that we mentioned the last time,
it denotes the irrational number called the natural exponential, and its approximation is 2.718. So log base e, that has a lot of applications in science and nature, so that's very common in scientific. It's also the logarithm that's used most frequently in business calculations.
Of all things.
Of all things, yeah.
But it's called the natural logarithm.
I asked a programmer, a TI programmer once at a class reunion, trying to scratch around and find something to talk to these people you haven't seen for 10 years, and you didn't know them that well. You weren't that fond of them.
You weren't friends back then, but now that we graduated and it's 10 years later, we're supposed to all be friends.
No,
of our case, it's 40 years.
Back in like 1992, I guess 96. Well, I was just teaching logarithms, Paul, and let me ask you something. Why is LN so much more popular than LOG nowadays from a programming point of view? And he was like, smaller base. 2.7 is smaller than 10. And I was like, oh, okay. It didn't seem that significant to me. But that ln is there are some high-end calculators that don't even have common logarithm keys on them anymore. They only have natural logarithm keys. So y'all can figure this out. This goes back to one of the first things that we wrote on Monday. 7 to what power is going to give you 1?
Let me write my thoughts. Here's what to try to figure out this number here. Here's what I'm thinking. 7 to what power equals 1?
Not 7 to the first. 7 to the first is 7.
0. That first rule we stated
on 0 exponent.
Oh wow! I just remember when we used to have to write on boards and stuff. I hated not being able to refer back. I love this now. Just okay. Remember what we did on Monday? That very first rule.
We wrote down. Okay.
7 to the 0 power is 1. Therefore, log base 7 of 1 is 0. Okay. Now, I'm going to... well, you know what? Was there anything special about 7? What if I'd written this? Just log base b of 1. Log base b of 1.
B to what power is equal to 1?
0.
B to the 0. So it doesn't matter what that base is. The log of 1 is always going to equal 0.
If someone says, oh, tell me a logarithm rule, you can say log base b of 1 is 0. Right? Anything to the 0 power is 1. Think about that. This is the exact same thing as this. They mean the same thing. It's just two ways of writing the same statement. And that's how I wrote it over here on Monday. The first thing, b to the 0 is 1. Here's another way of writing the exact same thing. But just notice, with exponents, the 0 is written small. When you write it with a logarithm, the base is the thing that's written small. And you might think, why does he carry on about that? Oh, it's just the same way of writing, two different ways of writing the same thing. Now, let's have I'm going to state another rule here. Log base b of b to the x.
This is something y'all can help us figure out. If you understand the definition, what power do we put on the base to get b to the x? B to what power equals b to the x? I remember the teacher saying once, when I first saw this property, I remember Dr. Robertson saying, it's sort of like who's buried in Grant's tomb. And I was like, oh, I don't know. Maybe there's a lot of different people buried in Grant's tomb. Do y'all understand the point she was making?
Who's buried in Grant's grave? Well, Grant. It better be Grant, right?
B to what power gives you b to the x? It should be obvious. Not
X.
1. B
X.
to the x. What exponent
B
do you
to
put on
the
b to give you
x
b to the x?
Is b to the x.
Think about what's just happened there. This goes back to something from last week with inverse functions. We performed the exponential function and the logarithmic function consecutively, and what did they do?
Canceled out.
That sounds like inverse functions to me. If you perform the two functions consecutively, they cancel each other out.
This was a week ago today, where we were doing fog x equals x and golf x equals x. If they cancel each other out, then those are inverse functions.
You started with x, and you end up with x, okay? You performed the functions consecutively, and you ended up where you started.
So a logarithmic function and an exponential function cancel each other out. Let's see. Another way of writing this, same thing. It's like
It
this.
doesn't matter which one's written first. Remember, if they're inverses, it doesn't matter the order. They're going to cancel each other out if they're performed consecutively.
B, oh, this looks sloppy, doesn't it? B to the log base B of x
Is equal to
x. They cancel. Exponents and logarithms cancel each other out. Okay, these are another way of saying it is exponents and logarithms are inverse functions. Oh, if you want to
write
say
that down
something,
there, right there.
you know what I'm going to say?
Yeah, exponentials and logarithmics are inverses. You can mention that, say you're just trying to find something to say to somebody and you want to get rid of them. You can say, oh wow, I just learned that exponentials and logarithmics are inverse functions. You want to talk about that? They'll go on their way pretty quickly.
Okay, I think maybe now we're ready to actually do a problem. But these two things right here, these two statements, are going to be very important.
Not just in this assignment, but in the
next assignment.
on the Monday assignment as well. So here we go. Number 1.
It says, solve this logarithmic equation, x equals log base 3 of 1 over 27. I'm going to change up some colors here. Okay. When it says solve an equation, hopefully you've gotten to the hang of this. If it says solve an equation, then that means get x equals some number. We want x equals some number. Well, we don't want this log base 3 here. We just want the x by itself, it's by itself, and we just want a number over here, not this log base 3. Well,
remember, if you can get the base of the logarithm equal to the base of the exponent, all that stuff cancels out. So we have a base of 3 on the logarithm. We need a 3 to the power here. If we can write this number as a 3 to the power, then
all of this, I want all of this written with just a big 3. Why? So they'll cancel out. Once this number and this number are the same, they cancel out. All of that will cancel.
And whatever that exponent is, that'll be your answer.
So let's think about how to rewrite 1 over 27.
Right over here on scratch work, I would write that's 1 over 27 is 3 cubed. 3 times 3 times 3. You agree? Let's see.
But
y'all agree 3 times 3 times 3 is 27? Yes? So that's, how do you write that 1 over 3 cubed just as 3 to the power? It's one of the things we were doing the last time.
Make
it a negative exponent. Good.
That was one of those things I said, I tried to review as soon as we started this. Okay, let's see. If you have a 1, like here, 1 over 4 squared, write it as 4 to the negative 2. 1 over k to the 9th is k to the negative 9. So I've thought of 27 as 3 cubed. And then the red 1 over became that red minus. Now we still have an x on the left, and that's good. Because we want just x equals a number. Cancel. All of that gets canceled, leaving us just the negative 3.
And how can you do that? From this, what should hopefully become an obvious statement to you. This is asking you b to what power gives you b to the x? Well, the x power. 3 to what power will give you 3 to the negative 3? Negative 3. The logarithmic to the base 3 and the exponential to the base 3 cancel out, leaving you just that exponent. Any questions there? Okay.
Type in negative 3 and let's look at the next problem. Number 2.
Uh-oh, I said to add this to your bag of tricks.
X.
When you run into a radical with a logarithm, you have to rewrite that radical how?
Oh, wait.
It's a log base 5.
I know. You know what?
Mark that all out.
Y'all can't see yet what I did. I messed up. I miscopied. And so...
Well, this is a big problem.
Oh, I know. Mm-hmm. Okay, I'll do that to cover it up.
Realize what it's really asking is 5 to what power gives you the cube root of 25. That's what it's asking. What exponent do you put on 5 to give you the cube root of 25?
It goes through.
We have a starting point. If you see a radical, you have to rewrite it. How do you rewrite a cube root using an exponent? Is it a -3? No, what is it going to be?
Let's see. Okay, since there's a small 5 as the base, in order for this logarithm to cancel out, we need a large 5. So we're going to write large 5. And then something else I tried to review at the very beginning. The bottom number is the root. The top number is the power. What would the power be? To get a 25, it's going to be 5 what? Squared. Now it's a cube root, so what's the bottom number going to be? 3. Okay? So
You're just making this
25.
work, Tony.
Yes, I am making this work out.
That's right. We're making it work. We know we need a 5 here to cancel out that log base 5 there.
Mhm.
So you do whatever it takes to rewrite that step there. The argument is 5 to the power. So you follow the logic. Look back at that problem from the last time.
Which problem?
The one with the fractional
Fractional
exponent.
exponent. Okay.
Because it's exactly what you were doing there.
Okay. 4th root and then cube it. Okay. So 4th root.
That
cube.
number there, the root, that root becomes the denominator of the fraction.
The power is the numerator. 5 squared.
So what's about to cancel out?
I'm about to write x equals what? 2 over 3. All of this cancels. And you might be thinking, well, wait a minute. What if instead of 25, there was
26.
something that you couldn't do? Okay, we'll answer all of that later eventually.
Something called a change of base formula. But for the time being, you have to be able to get a common base.
Okay, so type in 2/3. So we're solving logarithmic equations. Number 3. X equals 10 to the log.
Look at that. I don't see a subscript on that LOG. What do we assume the subscript is? If you see an LOG and there's no subscript, what do you assume the subscript is? 10. Okay. If
Right
there's
here.
no subscript,
Right, they can't see
wait.
it.
If there's no subscript, you assume it has a subscript of 10.
So I'm going to put a little 10 there.
I think this one's easier than the first two. I know the answer without showing any work. What does x equal? 7. It doesn't matter the order in which the exponential and the logarithmic are written. As long as they're written consecutively, they cancel each other out. And in this case, they leave us, what was the argument, 7?
So we just have x equals 7. They can't all be that easy. Now, generally, X that out and say similar, because I don't think, like on this one, notice, it didn't have that 10, and so it actually had to write out log base 2, what would the answer be here? 8. And if you're thinking to yourself, wait a minute, what if it were 3 to the log base 2 of 8 or something? What if those weren't a common
Then
base?
they don't cancel out.
But like number 4 will illustrate why I say that you're going to have a common base. Looking at number 4, how the heck is number 4 is different from the first 3? Well, how? Well, in the first 3 problems we've done, the x was already by itself.
Okay, x is by itself, by itself.
But here on problem number 4, the x isn't by itself. If we're going to solve an equation, we've got to ultimately get x equals number. Well, the x isn't solved for. See, we have all that log base 5. So somehow or another, we need to just get the x by itself to have x equal a number. How will we do that? Well, going back to this idea of canceling, like right here, there was a big 10 and a little 10, they canceled out. I'm about to write a big number right here that'll cancel out that logarithm. What big number would I need right here to cancel out that logarithm? 3? No, not 3. It's got to be...
I thought I heard 5.
5? Oh, okay. Whatever the small base is, just put the big base there. And if you do that to one side, you've got to do it to the other side.
Now, before we go on, why are we able to do this? It goes back to what we were doing the last time. When we were solving those exponential equations, remember we'd get the same base equal, and then you drop the base and set the exponents equal. Now we're doing it in reverse. Here are the exponents that are equal. Those blue things are exponents. We'll put on the common base. That's why we're allowed to do this, what we're just doing, because it's just the reverse of that property we were using the last time. If the bases are equal, the exponents have to be equal. Now we're going backwards. If the exponents are equal, that means the bases are equal.
No, don't say 15.
5 times 5 times
This is
5
now.
is...
Let me write it neater. It's 5
125.
to the third. And did I hear 125?
Mm-hmm.
You'll see, at this point, the blue stuff is exponents. So we have 5 to the third. 5 times 5 times 5, 125. So if you're sitting there wondering on number 3, how would I do that if this were a 10 and this were a 7 or something? The bases weren't the same. You wouldn't ever have that.
Because you're deciding on the base yourself.
Why would you put a 6 as the big red number when it wouldn't cancel out that base right there? You're deciding what number to put here.
We'll be doing more of this in the next homework assignment when we start solving some messier logarithmic equations.
But it's still the same basic idea.
The same idea. You're right.
Now, I need to. Okay, don't panic yet. Okay, there's 3 rules of logarithms that are so important they have names, and I'm going to state those rules. The first one is the product rule. Log product means what? Add, subtract, multiply, or divide.
Multiply. Right.
Multiply.
So m times n. The log of a product.
The log of a product. And I'm stating these without a lick of proof. If we had enough time at the end of class, we might. I'd always like to go through and derive those rules, but you'll have to be really dedicated to wait around. Log base b of m times n is log base b of m plus log base b of n. So what it says is if you have the log of a product, you can write it as the sum of 2 logarithms. There's another good thing. If someone wants to talk math with you or something, tell them the log of a product is the sum of 2 logarithms. Right?
Okay, and you know something? We're not going to do a formal proof, but I want to point out something to you, okay? That's just interesting. This is the product rule of logarithms, what we have here. There's something called the product rule of exponents. The product rule of exponents says b to the m times b to the n. Can you all see that? If you have repeated bases, you add the powers, b to the m plus n. For example, if you had x squared times x to the 5th, that's the same as x to the 7th. 2 x's, and then 5 more. 1, 2, 3, 4, 5. How many x's do you have total? 7. If you have repeated bases, you add the exponents. Look at this. We have let's see, that's the product rule. You have repeated bases, you add the powers. Here you have a product, you add the logarithms. Remember, logarithms are just a fancy way of saying exponents. We're adding the exponents. If the logarithm has a product, you add the logarithms. If the bases have a product, you're multiplying those bases, you add the powers. So there's a very strange connection between the product rule of logarithms and the product rule of logarithms and the product rule of exponents. And let me show you something else.
What?
Tony's about to state the quotient rule. If I show y'all the quotient rule of exponents, if I remind y'all of the quotient rule of exponents, I bet y'all will be able to figure out this quotient rule of logarithms.
Yeah, but even if you don't, if I just tell them, when you multiply, but if the product rule says if you have log of a product, you add, what would y'all guess we're going to do with a quotient? Quotient means division. Subtract. See, they don't even need to be reviewed that. But you're right, it follows right from that.
It's a direct result, and we're just restating. That product rule is just a logarithmic restatement of the product rule of exponents.
If you had b to the m over b to the n.
This is the cancellation property. The quotient rule of exponents is just the cancellation property.
Like if you had x to the 5th over x squared, what would you do to those exponents?
Cancel 2 x's above and below, and how many would you have left? 3.
And so,
repeated bases being divided, you subtract the exponents. Argument being divided, you subtract the logarithm. Repeated bases being multiplied, you add the exponents. Arguments being multiplied, you add the logarithms.
Well, that makes it clear to you. Now, suppose we have an exponent at the end of the logarithm. That's what the power rule is.
This is probably the most bizarre looking property of logarithms, but it's the same as the power rule of exponents that we used the last time. You go ahead and state what it is, and then I'm going to show them, remind them of the power rule of exponents, because
if you have an exponent at the end of the logarithm,
it has to be applied to the entire argument.
It's all at the very end. You can move it down in front and write it as multiplication.
So it becomes a coefficient.
N times log base b of m. The power rule says you can take the exponents, move them in front of the letter L. Okay? And that's a direct result of
the power rule of exponents. We call the power rule of exponents. I don't remember what letters we were using the last time, but if we have something like b to the m raised to the n power. If you have a power raised to a power, what do you do? I recall this happening the last time. What did we do? A power raised to a power. Right here, number 23. Right there, a power raised to a power. What did we do?
Well, what about
right here.
That's
the
a better
X,
one.
that's a better one. What did we do there?
You
You multiply, okay? So if there's a sum or difference, you distribute. But the general answer I was looking for was multiply. A power raised to a power, you multiply, okay? M times N. I said a logarithm is just a fancy way of expressing an exponent. A logarithm is just an exponent. So we have an exponent to a power. Well, a power, the logarithm's a power. That number there is a power. A power raised to a power. What do? You multiply. You're multiplying the two powers, the n power and the log base b of n power.
Now, we've talked so long, we're going to wind up getting logged out. So go ahead and come over back to problem 5. Don't panic when you see this. What I'm going to do, we're not going to do this problem yet, but just go on to the next one. I just want the screen to stay active so we don't lose it. We're going to start doing something called expanding the logarithm. Okay? Number 6 says,
sometimes the instructions just say rewrite the logarithm, but what we're going to do, don't write this down. We're going to take a single logarithm and write it as a sum or difference in multiple logarithms. That's called expanding. Why don't you write that down right now, Tony?
I'm just going to write how to expand a logarithm.
When you're expanding a logarithm, you take a single logarithm, one log, and you write it so that it has multiple log notations. But in the process, the argument's a lot easier.
So I'm going to go through and show y'all how to expand the logarithm using the 3 rules: the product rule, the quotient rule, and the power rule. I'm going to show all the steps just like they do in View an Example. And then once I'm through doing it, I'm going to see if y'all could figure out how to do it with just one step.
But to realize what we're going to do, there's a sequence, an order to what we're going to do.
I stated the product rule first, but really the first thing you'll do is use the quotient rule.
And make a note, use that quotient rule if the argument has a fraction in it. There has to be a fraction in it to use the quotient rule. M over n, something with the fraction bar in the argument.
Then after you use the quotient rule, you'll use the product rule. Now the third step I'm going to leave blank right now because I'll see if y'all can figure that out. And then the last thing you do is use the power rule. So I remember the semester the student told me I should have written, but I stated them. I should have stated quotient rule first, then product rule, then power rule. And yeah, I mean, maybe I should have. That's the order I'm going to go through. Quotient rule, product rule, then a third step. I'll see if y'all can figure it out, and then power rule. And I'm going to give you an example. Expand the logarithm. And here it's log base 3. Now I'm going to write a lot of messy stuff right here. X squared y to the 1/4 over w to the 4th, and I would need another variable. How about a to the 1/2? Okay. We're going to expand this, going through those steps. The goal is to write it so that we don't have such a big mess after the logarithm. We would prefer just one letter after the logarithm. Instead of an x squared y to the 1/4, how would we write it as 4 different logarithms with just one letter after each logarithm. That's what expanding means. Well, the first thing we do, we use the quotient rule. The quotient rule says
the log of a fraction is equal to the log of the numerator minus the log of the denominator. Okay.
And so I'm going to now rewrite this log base 3 of the numerator, x squared y to the 1/4, then a minus log base 3 w to the 4th a to the 1/2. So that was just the quotient rule that I just used. I went log top minus log bottom. The next thing I'm going to do in purple is use the product rule, but I want to go ahead, since it's a product rule, let me put the dots to indicate the multiplication.
X squared is being multiplied by y to the 4th. We have a product, so we can split up that product as the sum of the two factors.
In fact, we're going to be using the product rule twice. You use it here. You write it as log base 3 of x squared, and then a plus log base 3 of y to the 1/4. So that was the product rule. Just bear with me. You'll be amazed in a little bit that you can do all of this in one step. Now, I'm carrying down that minus.
What I like to do, just to make sure I realize it, all the stuff that came from the first logarithm, I enclose in parentheses, okay? And then for the second logarithm, I enclose all of that in parentheses.
So how will I rewrite this second logarithm? Log base 3 of w to the 4th, and then a plus. I'm rewriting that multiplication as addition. Log base 3 of a to the 1/2. So we use the quotient rule. We use the product rule. I didn't state the third step, but the way Tim wrote these parentheses here, we have a minus here. What am I saying or trying to hint at very poorly that you're going to have to do?
Tony would have put those parentheses after the minus, okay?
Yeah.
But he would have done that automatically. I put the parentheses around the first one also to make it more obvious. Well, the first set of parentheses, there's nothing in front of it to distribute.
You've already said it.
I said it.
What am I trying to get y'all to say the third step is? What? Distribute the minus. That's okay.
Okay.
Distribute the minus. Okay. Now, so I have log base 3 of x squared plus log base 3 of y to the 1/2. 1/4, I'm sorry. There's no, I don't need those parentheses there. There's nothing to distribute except a +1. But here, we distribute the minus, so I'm now going to have two minus signs. Minus log base 3 of w to the 4th, and another minus log base 3 of a to the 1/2. I hate to say, are y'all following what I'm doing, but
keep in mind, he's almost ready to write the final answer. And what we're going to start doing is going from the original problem. Now, if there were any radicals, I'd add in a second step. If this had been written with a radical, say a fourth root, I would then have the step where I rewrote everything with fractions, the radicals with fractions.
Like this 1/2 would have been what sort of root?
If it had started off as a square root, you have to rewrite it as an exponent of 1/2. But otherwise,
there's one step left now. Use the power rule. The power rule said if you have an exponent at the end of the logarithm, move it to the front of the log, the letter L.
Realize you couldn't have done that to begin with because there's not an exponent. When you had that huge argument there, there's not one exponent out here being applied to every one of them. So, but now, each exponent is only being applied to the one factor that's in the argument.
Eventually, you're going to wind up having to type stuff like this in. Okay. It'll take you longer to type in your answer than to get your answer. Looking at the final answer and the original problem.
Yeah, wait, let him finish writing it down. Because the first thing, I always ask myself, when I'm looking at a logarithm and I'm going to expand it, I ask myself, well, how many logarithms will I have in the expansion? Each individual factor gets a logarithm. On top we have x times y, so we need 2 logarithms. How many factors here did we have in the bottom? W times A, there are 2, so that's a total of 4 logarithms we need in our final answer. Well, where do these exponents go? Once you decide you need 4 logarithms, 1, 2, 3, 4.
Exponents go in front of the letter
They become
L.
coefficients. Well, what about these signs?
In particular, the minus.
Yeah, what about this plus sign here, especially the minus sign here? Where do these minuses come from? Why do we have minuses in front of those last 2 logarithms? Where do the W and A start off? In the bottom. So that minus from the red fraction bar in the original problem, it had to be distributed through the logarithms. So I think we could say if the factor is if the factor's in the denominator, that logarithm will be preceded by what? Plus or minus. If the factor starts off in the denominator, then it's going to be preceded by minuses. If the factors start off on top, well, I don't see a sign in front of that 2, but what do you assume it is? Positive and a positive. The factors start on top, they're preceded by positives. The factors on the bottom, they will be preceded by minuses. The arguments are the individual factors, x, y, w, and a, and the exponents become coefficients.
Wow, so that makes it perfectly clear. So, separate at multiplication and division. The stuff on the bottom will have minuses in front of them. The stuff on top will have pluses, and the exponents go in front of the letter L.
We have a product rule, we have a quotient rule, we have a power rule. We do not have a sum or difference rule. At this point, I like to write up log base b of m plus or minus n cannot be separated. If you have a plus or minus in your argument, you're going to be stuck with that plus and minus.
Separate at multiplication and division, comma, not addition or subtraction.
If you have a plus or minus in the argument, if you have a plus or minus in the thing that follows the log notation, you're going to be stuck with that plus or minus in your expansion.
And we'll see that in a moment, but let's just make sure that y'all get the hang of, let's
I'm ready. I want to do one. I'm going to do one, Tony. Let me do this one.
No, I'm going to make up one first.
I think
and
we can do this one. I think we can make up this one and do it.
Log base.
Oh, wait. Let me switch it since you're making up one. Make one with the radical. Oh.
I just want to make sure they get the hang of the...
Okay, you're right.
Log base 2 of a to the third, z to the fourth,
and on top
c to the ninth, over the number 5, w to the 1/2, and...
That's enough. That's enough.
I'm just going to add one more letter.
You're right. We're not going to have to type this, okay? So
d to the 6th. Okay.
Don't say anything and don't give it away, Tony.
Oh, I'm going to give it away. That's sort of my job, to teach them, show them how to do that.
Okay, I'm about to ask a question.
Oh,
I don't want you to give it away.
Distribute. When I was working up to that earlier, you up and said it. Okay.
Okay. How many separate logarithms are we going to need for the top? How many distinct factors are there? How many things are being multiplied on top? 3. So we're going to need 3 separate logarithms in the expansion. Now be careful on the bottom. How many separate factors do we have on the bottom? How many things are being multiplied? 5 times w to the 1/2 times d to the 6th.
3.
Another 3. So 3 and 3, that means we're going to need 6 total logarithms.
How many negatives are we going to have in this problem? 3. One in front of everything that's in the bottom. I remember this.
I'll write out the log base 2. Log base 2. I like to write it all out.
Well, I'm just going to start right off.
Okay,
writing.
Right.
We're now going to write out the answer. The exponent goes in front of the letter L. Log base 2 of a. So
plus or minus? What's the next?
Plus. The z is on top, so it's a plus. The exponent goes in front of the letter L. So plus 4 log base 2 of z.
Plus or minus? Plus. Okay.
9. The exponent goes in front. Log base 2 of c.
Plus or minus. Because we're moving down to the denominator. And once you move down to the denominator, you never change back to plus. Because you've already done everything that's on top. So it'll be a minus.
No, be careful. Sometimes people think the number goes in front of the letter L. No, no. The exponent. Is there an exponent on this 5? Say no. Well, theoretically there's a 1, but we don't have it written there. So nothing's going to go in front of the letter L. It's just going to be...
There's no coefficient on this logarithm. So it's just a minus log base 2 of 5.
Yes.
Plus or minus. And okay,
minus.
A common problem is people put the first minus, but then they don't distribute and they start back with the pluses. Once you start the minuses, it has to stay a minus. Everything else is in the denominator, so it's going to be preceded by a minus.
Minus.
Okay, plus or minus, minus. Okay, Tony answered.
And then 6 log base 2 of d. I'll sort of see how I did that. And you might think, well, wait a minute, all you did was write the problem and write the answer. Yes, that's what I did. That's easier in the long run than going through all of these steps. And I have to give credit. It was my brother one day when I was doing these logarithms, where he was also.
Doing that in 1990,
and I was going through the steps like they do it in the book, and I'm viewing example and stuff.
I was like, what are you doing, Tony? I mean,
and he said, it's easier if you just don't show any steps. Just have them do it. And I was like, no, they want to see steps. And I tried it, and I was like, oh, wow.
Back then, there were a lot of differentiating logarithms. I remember at Baylor, they had so many messy logarithmic functions to differentiate in that book.
Now let's do number 5.
I'd gotten real. I was like, okay, we're just going to do it real
Move that
fast.
calculator.
Expansion.
Close that
I'll do this
calculator.
one. I have it. I'm hiding the
Okay.
choices. Okay. I'm going to do one, then I'll switch back. Okay. I'm going to do this one. I've just been aching to expand a logarithm. Okay.
Now, this one is different from the ones I just finished doing because we have the radicals. There's a square root. Well, heck, there's two square roots, and there's a cube root even. So you're going to have an extra step on this.
Okay.
That's
I
a
want to
cube
point
root of
out
y.
something to y'all. Okay. Notice how that 3, it's right over the hook on the radical. That 3, that's saying a cube root of y. That's not saying you're cubing the square root. That's a cube root of y. Look down at the bottom. Is this a 7th root of z? Is that 7 right over the hook? No. So that's just a square root of z. But it's a cube root of y. A cube root of y. And we have a w to the 7th, and then a square root of z. Okay.
Okay.
Oh, yeah, you're right. That's a bad thing. Oh, there.
Okay, we have one extra step that he's just going to do maybe off to the right. Like equals right here and write it out with the fraction.
Oh, I'm going to. I'm going to do it right here. Log base 7, I have one extra step versus the one that we just did a moment ago. This is that thing I said you got to add to your bag of tricks. If you have a logarithm with the radical, you have to rewrite the radical using an exponent. The square root of x is the same thing as x to the 1/2. A cube root of y is the same thing as y to the 1/3. And that's a w to the 7th. And the square root of z is the same thing as z to the 1/2. How many separate logarithms are we going to need? 4. We have 2 separate bases here. Factors. X times y. Notice I'll make the red dot right
I'm more
here.
fanatical about making those dots than my brother is, I think. But once I remember students saying, you seem to think these red dots and stuff are important. You draw them as if they're important. And, I was like, yes, they're important. That's where you separate. You separate at multiplication and division. Okay? Why is this fraction bar red? Well, 1, 2, 3, 4. How many minus signs are we going to have?
2 minus signs.
At this point, most of you, I think, could look at the 4 answer choices and choose one.
But we're not going to do that. I'm going to write it out. Okay, first of all, I'm going to deal with the x to the 1/2. Am I going to have a coefficient? Yes, what is it? 1/2 log base 7 of x plus or minus. Plus because we're still up on top. So a plus. Am I going to have a coefficient? What is it? 1/3 log base 7 of y plus or minus. Minus because we're moving down to the denominator. Am I going to have a coefficient? What is it? That's 7 log base 7 of w plus or minus. Another minus. Remember, once you move down there, it doesn't switch back to plus even though those are multiplied because that minus has to be distributed. So once you switch to a minus, it has to stay a minus. So minus coefficient 1/2 log base 7 of z.
Okay, so let's look at the answer choices.
Clearly not A.
Not
B.
A.
What about B? B is looking pretty good. What do y'all think? B?
Is it B?
Look
Oh,
at
wait.
D. Let's see what D is. No.
That's where I usually mention that once we're through with this. So which one is it? It is B?
Oops. Okay. There's that answer choice. This cannot be simplified. To illustrate.
Remember he said you can't separate at addition or subtraction. And I said I like to write note log base b of m plus or minus n cannot be separated.
Oh, Tim. S-E-P-A-R-A-T-E-D. I can see you didn't get the spelling award. You got that penmanship. So you could write your words real pretty, but you couldn't spell them right. I got the spelling award. So together we were really a good team.
I know. You could spell the words correctly, and I
could
could write them
real
pretty.
Okay.
Any questions there?
Now flip over and do this. Make up an example, and here I'll call it out to you. Example.
Okay. Example.
Log base 3, parentheses.
Is there going to be a fraction?
No.
Okay.
A square plus w to the 5th minus d to the 3rd.
You can only separate.
Can I put the red dots there?
Can I put the red dots or the red fraction bar?
It can't be separated.
Cannot be. I think the option they're using is cannot be simplified.
That's what option D said on the multiple choice. Here's one. You can't separate. That's why those dots are important. If you can't put the red dots there for multiplication, it can't be separated. You don't separate at addition or subtraction. Is that clear now? What we mean by can't be simplified or separate at multiplication and division, not at addition or subtraction.
Are we about to start typing in the ones?
Let's do number 6.
Okay.
Now this is one you might be able to just type it in, but I want him to write it so he can write the red dots and draw the red fraction bar.
Base B of
X to the 3rd y
all over Z to the 3rd. Okay. Oh, and I didn't box in my final answer on the previous problem.
Oh, when it's that long.
Pop psychology, boxing in your answer says that you're through with the task, you've finished an unpleasant task, and you're ready to move on to another one. So that's why I like to box or circle my answers. And
how many logarithms am I going to have in this answer?
3.
How many minuses?
Just one.
Can y'all call out the answer?
Call it out.
First, put the red dot.
Okay, where does the red dot go? Y'all tell me. Okay, the x cubed times the y. So we can split at the red dot and at the fraction bar.
Doing the red dot.
No, but here's what I like to do, Tony. Look at this. I like to write out my 3 logarithms. No, you don't do that. I know you do. I like to write it out, and then where does that 3 go? In front. What's the argument? Plus or minus? Plus.
Because the y is on top.
Because the y is on top. Coefficient, do we have one? No, because there's no exponent. Argument. Plus or minus? Minus, because we moved down to the bottom, so we're going to have a minus. Do we have a coefficient? 3, I agree. And the argument is there. So 3 log base bx plus log base by minus log base b of z. Remember the time I had this.
Okay, I'll type it. We can switch back now, okay?
You're getting them right, so you go on. 3. Okay. Oh, you want to do that typing because notice how the log is bolded. You have no idea how many times I get emails from students. It's not bolding. It's not bolding. If you're typing it correctly, when you type log, notice what just happened. Look, you see 3. I'm typing lowercase l, lowercase o, lowercase g. It's going to space it correctly and bold it.
What's the argument next?
No, I got to put the subscript.
Oh, yeah, you're right. Okay. Oh, goodness. And then you got to get out of that subscript position. Notice, I don't think we've used the subscript key before. We've used an exponent key. And notice how the exponent key always says superscript, and I've said it should just say exponent, but it doesn't. Now we're using, do you see the gray box with the blue box underneath it? That's the subscript key, and that's what you're going to be using. Now I use the little shift up arrow as an exponent shortcut. What do you think the shortcut is for the subscript? Shift down arrow? Yeah, that's what I do.
Look what's about to happen. I just typed what looks like log and it didn't bold it. That means something's wrong.
Well,
what was wrong?
Let's see. Let's just type it. Maybe it'll give you the correct answer, Tony. But you got to get out of that subscript before you type your y. Minus 3
Go ahead and type it.
Log. Oh, there it bolded. So maybe it's gonna
Put subscript B.
Get out of the subscript and a Z. What do you think? You think they're going to count it right? The only problem is that our log there doesn't look like it's bolded. Maybe you should take a screenshot of it and send it to me.
Wait. Okay. Look at this.
Oh my Lord!
Oh my
I can't believe it.
Although your answer is equal to the correct answer, it is not in the correct form. Be sure to read any instructions. Your answer contains an uppercase I followed by the letters OG.
Oh, I can't believe it.
Oh, wow. Okay. So, for years, I've waited for them to get this sort of warning.
We've even mentioned that to the Pearson reps who aren't programmers. The people we deal with, they're not programmers. They're just salesmen.
I wonder if they actually, I've written little suggestions and stuff, and I've told them that. You know, they need some sort of warning. What was wrong here? I hit a capital I rather than a lowercase l. So I'm going to back it up. Lowercase l. Wow. Notice it's bolded. Oh, wow.
I'm as excited as I was the day that I saw that plus minus heart button. I have to say, it's a shame that that's what my life has become. Okay, I'm excited about this. Wow.
Okay, let's do number 7.
Okay.
Notice it just says log, so we assume it's a base 10, but for typing in purposes, you don't have to be typing in the subscript.
Log.
That's an 8th root.
8th root.
And it's the whole thing. Wait, the A over B are both under this.
I know.
Oh, okay.
The common log of the 8th root of A over B.
An 8th root is the same as what fractional exponent? 1 over 8. But wait a minute. Is that 1 over 8 exponent only on the A, or is it on both the A and the B? It's on
both.
Also.
A and B are both both under that radical, so they're both going to have a 1/8 exponent.
So you write log A to the 1/8.
A to the 1/8 divided by
B to the 1/8.
B to the 1/8.
Here, I don't write any dots, do I? Could y'all just call it out? There's going to be 2 logarithms, so it's 1/8.
Okay, you bring down the 1/8, and then we have the log A plus or minus
coefficient, 1/8 again, log B. That's a funny looking B, isn't it?
It's sort of like a 6, but I know it's a B.
It's a B.
Let me see. So 1/8 log A, 1/8, right arrow. Notice we don't have to type in the subscript, just log A. Now, I remember one time on this particular problem, a student asked, well, what if you put log base 10? Will it count it?
I don't know. Let's see.
No, it counted it wrong.
Oh, type it and see.
Oh, okay.
LOG. Suppose you put that subscript
10
and then
B. So I've typed it in with the base 10 just to see will they take it or not. But one semester they wouldn't.
No.
Oh.
It's equal to the correct answer, but not in the correct form. They don't want you to show that subscript of 10.
So there. Okay.
Okay, keep going.
Okay, log base F. There's one thing we have to do before we start drawing our red dots. What's that going to be? Before we start expanding, there's a square root in there. So, what are y'all thinking I'm going to have to do with that square root of x? How do I write it without the square root? X to the 1/2.
You know something? If you're feeling lazy, we don't have to rewrite all of that. We could just write it right up here. It's x to the 1/2 and just sort of mark out that square root of x.
Now, how many logarithms are we going to have?
How many separate factors do we have on top? 2, x and y. On bottom, 1, so that means we're going to need a total of 3 logarithms. Let's get started. Coefficient.
Put the red dot.
Oh, yeah, you want that red dot. Good right.
That's where it separates.
Okay, so that's where it's going to separate. Okay, will the first logarithm have a coefficient? If so, what is it? 1/2 log base f of x plus or minus, plus, because we're still on top, coefficient log base f of y plus or minus, minus, because we're moving down to the denominator, coefficient 5 log base f of z. Once again, if they show a subscript, you have to type that subscript in your answer. If you accidentally dropped that f, then you would be changing log base f to log base 10, which you can't do.
So it's 1/2, get out of there, log base f, right arrow x, plus, I remember years ago, this wonderful student, she was always joking around in class, and she said, oh, it takes longer to type in the answer than to do the problem. And I was like,
yeah.
And then a minus 5 log base f of z.
That looks right. Okay.
Any questions? Well, here's my, okay, but this problem's going to have the ln, the natural logarithm, okay, so I'll put on there, if it's not bolding, then you're typing a capital I instead of a lowercase l. No, that's it. Okay, let's see this problem. Oh my gosh.
Oh. Okay.
You'll be able to impress yourself.
Okay. The natural log.
It's an ln, not an in.
Oh, is this a sixth root? What does that look like? Is that 6 right over that little hook there? No, it's not a sixth root. That's x to the 6th times, I'm getting lazy. I'm going to rewrite, I'm not even going to write down the radical. I'm going to convert it immediately to an exponent.
Square root is the same as what radical? Oh, what exponent?
So you have x squared plus 2. You have x squared plus 2. Notice how I'm going to write this. X squared plus 2 to the, what was the square root?
1/2.
1/2, okay. And what have we got on the bottom?
And x plus 2 to the 6th.
So there's 2 6 exponents.
Oh, yeah.
I like LNs and LOGs, although I think it's going to get to the point where they drop that notation. Just because, well, with modern equation editors and stuff, it's easy enough to type the subtitles. I mean, the subscripts, that's what they're saying. But I still prefer, it's still quicker to type just an LN rather than an LOG subscript V. So I hope they don't get rid of this notation, at least not for the next 10 years before we retire, okay? So,
okay.
You cannot separate pluses or minuses. If you have a plus in the argument of the original problem, you're going to have that plus in the argument of your final answer. I see 2 pluses. I see an x squared plus 2. That means I must have an x squared plus 2 in my final answer. I see an x plus 2. I have to have, that has to stay together. You cannot separate at addition and subtraction. You can only separate at multiplication and division.
How many LNs are we going to have here when we separate them?
In our expansion, how many LNs will we have?
3.
We have the x, we have the x squared plus 2, and we have the x plus 2. So we're going to need...
We can't separate that x squared plus 2 and x plus 2. Go ahead and start it. I'll get you started. 6.
Okay, so we're going to have a coefficient of 6, ln, argument, plus or minus, plus because we're still on top. So we have a plus. Do we have a coefficient? If so, what is it? 1/2 ln, and we must enclose the x squared plus 2 in parentheses. If you don't include the x squared plus 2 in parentheses, you're only taking the natural log of x squared. So that x squared plus 2 is in parentheses. It has to stay in parentheses. Otherwise, you're not taking the natural log of the sum. You're only taking the natural log of x squared. Plus or minus? Minus. Do we have a coefficient? If so, what is it? 6 ln, and we have another set of parentheses with the x plus 2. If your argument has a plus or minus, you're going to have to enclose that plus or minus in parentheses.
So 6 ln x plus 1/2 right arrow ln parentheses x squared right arrow plus 2 close parentheses, then a minus 6 ln parentheses x plus 2 close parentheses. In algebra, you always do it one way, then do it in reverse. Let me see. Oh, well, another one of those.
We're now going to go backwards. We started off expanding. We took one logarithm, we wrote it as multiple logarithms. Now we're going to go backwards. We're going to take the multiple logarithms and write it just as a single log.
The formal name for this is called condensing logarithms. We're going backwards.
And remember, if it has a minus preceding it, where does the argument go? In the single logarithm, it goes on the bottom. If it has a plus, the argument goes on top. If it has a coefficient, where do the coefficients go when you're going backwards? The coefficients become the exponents. Okay.
So, number 10, it just says write as a single logarithm. So, there's only going to be one logarithm. I wish it had said condense the logarithms, but okay.
Surely you could make a better wish. I'm careful about that because I always worry. Suppose I say I wish that, and that's the one wish that, some divine deity decided to grant me. Okay, I'll give you that one wish. No, I got to be careful.
I just wished that. What did I wish? I don't remember. Okay, we want to write this as just one logarithm.
Okay, so there's
base 7.
Do I need a fraction bar? When I'm condensing, I always ask myself first, do I need a fraction bar? And when you look at the I switch over to my paper. You see, when you see that minus in front of the logarithm, you know you need a fraction bar. This minus here, you know you're going to need a fraction bar.
You make this minus red.
Oh, you're right.
You can indicate. Okay, because of this thing that now looks black, here's the red fraction bar. Be careful. You're not going to subtract the 13 and 10.
What goes on top? 13. What goes on the bottom? 10. Okay. There it is. Log base 7 of 13 tenths.
Now we're going backwards, doing this condensing stuff. 13 tenths. Okay.
Any questions there? But when I'm condensing, the first thing I ask myself, do I need a fraction bar? Okay, so let's look at number 11. You still have the little automatic. I think Tony put those in when he was
One
real
day
frustrated.
I was really frustrated. Oh, I've got, all these emails. Everyone's sending me the screenshot of it saying that their right answer was wrong and stuff. But now, with the warning that it gives them, hopefully that won't be a problem.
Hopefully, you're right.
So we're going backwards. We're going to now condense this down to just one logarithm.
Uh-oh. I see a plus or minus in an argument. That means that same plus or minus has to be in the final answer. That z plus 3, we're going to be stuck with the z plus 3 in our final answer. Just like here, I made that remark, but I never went back and reinforced it. I'd said, if your argument has a plus or a minus in the original problem, you're going to have plus or minuses in your final answer of the argument, okay? That z squared plus 2 had to stay together. The z plus 2 had to stay together. So we have, I'm writing my log base 7. First question, do I need a fraction bar? Yes, because of that minus right there says I need a fraction bar. What's going to go on top? Z to the fifth.
I'm so glad you said that. You have no idea how often students will say 5z. No. Remember,
don't even put that idea in their head, Tony. Okay.
And on the bottom, just z plus 3.
Normally I would enclose the z plus 3 in parentheses, but since it's all there under the bottom and there's nothing else to multiply it by or a power, you don't have to.
But
it wouldn't be wrong to type it in parentheses.
Because I'm going to because basically if there's parentheses to begin with, if you have the parentheses in your answer, that's fine. Okay?
Wait a minute. I got to box this in. That tells me I'm through with the problem. There. So it's log base 7.
Log.
Subscript 7. Get out of the subscript.
Yeah. Right arrow. I just put fraction bar. Z.
To the
raised to the 5th. Over. Now I'm going to put that z plus 3. I'm going to leave it in parentheses.
Uh-oh.
What did I
Is there
do
something
wrong?
wrong? Oh, it's a log base 7 for the subscript, not a z.
Oh my goodness. Oh, thanks. What the heck am I doing? Log base 7. Okay, there. Okay. Sometimes, if you look at the work, I remember, oh wow, it looks like I just wrote down the problem and wrote out the answer, doesn't it? If you want steps, look at view an example. They're going to break it up into a lot of steps, which makes it so much easier for you. I'm joking about that. No. Breaking this up into a lot of steps doesn't make it easier. Okay. Hey, you know what? Let's see if y'all can do this. Can y'all call it out to me?
Oh, I like this. It's a common logarithm. You don't have to type a subscript.
So I'll just write log. Will there be a fraction bar?
Yes, what's saying there's a fraction bar? That minus says we're going to have a fraction bar.
Mm-hmm.
What have we got on top? Are there going to be any exponents in our answer? Mm-hmm. No, because there are no coefficients in front of the letter L's. So
this is normally, if there's parentheses, you leave the parentheses, but since there's nothing except 3x plus 1 on top, if you want to put not put the parentheses, that's fine. And if you don't want to put the parentheses around the x, that's fine, because there's nothing else down there. But if you put the parentheses,
it's not going to count it wrong. So.
Uh-huh.
Oh, let's see. What are we
really?
doing?
They're going to do some work.
What is
wow!
This?
Okay.
Go back. What
N equals x. They say.
N is x.
I didn't know N was x. M was 7x plus 12.
Oh, they're identifying the M and N on the. Oh Lord.
Okay, well.
Oh goodness. Oh,
good. Oh, wait, we've had a There. Okay.
Okay, number 13.
1/6. What is that? Is that an I-N-Y? You do say I-N. It's L-N. And if you do say I-N, and someone asks you, who was your algebra teacher? And you remember my first initial is, wait.
No.
Don't. Yours. No, but anyway.
Okay.
Okay, so 1/6 LNY plus LNZ. Well.
Okay, let's switch over.
Are we going to have any
Am I going to make
bar?
a fraction bar? No fraction bar because there's no minus. So, okay, so we're not dividing. If you're not dividing, there's only one other thing you can do to arguments. What is it? There's no fraction bar because there's no minus. If you're not dividing, then you got to multiply y times z.
Oh, wait.
Where does that 1/6 go? Where am I going to put the 1/6? It can't just disappear.
The 1/6, I think they're thinking it, but they're not going to say it. The 1/6 goes on the y.
It goes up there as an exponent. So it's y to the 1/6 times z.
And this one's a little different because there's no fraction bar, and everything else up to this point's always had fraction bars.
I remember the old multiple choice problems. They would have y to the 1/6 plus z as an answer, and well over half the class would fall forward and choose that wrong and put a plus there. You're not going to put, the only way you're going to have a plus in the argument is if you have a plus in the argument of the original problem. Like on number 11, we had a plus in the argument of the original problem. We had that same plus in the final answer. Up here, we had pluses in the original problem. We had pluses in the argument of the final answer. But the only thing you can do to arguments is multiply or divide them. You're not dividing because that's not a minus, which means you have to multiply. Y times Z is being multiplied. 1/6 is the power on the Y.
So I type ln y raised to the 1/6 power. I don't really like the way they write that. I would have preferred the 1/6 with a slanted fraction bar, but okay. And then, oh wait,
Get out of that exponent.
Z right there, you see? Oh, let me go like that and a Z.
Any questions there? In order to have a fraction bar in the condensation, you better have a minus in front of one or more of those logarithms.
Gosh, I'm tired of these instructor tips. Okay, maybe this was a better one to do before 13. Because this problem's very, very similar to number 14. My brother's just going to write the problem down and write out the answer. If you were sitting at home doing this and you were good at it, you wouldn't need to write anything down. I'd write log base B. Oops. Log base B.
Okay, but they're writing on paper, so I'm going to write on paper.
Oh, they're writing on paper?
Well, actually, a few of them are using their rare Egyptian papyrus.
And maybe even a tablet.
Even a tablet, you're right.
Okay. That was one of those things we had to learn in school, that Egyptians wrote on papyrus. Oh, wow. That has been very useful to me throughout my life. They probably don't teach that anymore.
Do they teach that anymore? That Egyptians didn't have paper, they used papyrus?
That was something 50 years ago they thought was important. Not exactly 50.
Close enough.
Close enough. Yeah. Almost.
You're
okay.
Right. Do I need a fraction bar? No or yes? No, because there's no subtraction, no minus sign, so we're not dividing. If you're not dividing, then the only thing you can do is multiply, so you're going to multiply the x and the z.
Instead of the exponent, it's going to be on the x and the z.
7 on the x and 9 on the z.
Okay. Log base B of x
to the 7th,
right arrow,
z to the
9th. Again, it looks probably like we're just writing the problem down and writing the answer. Well, if you want steps,
they're an example. Okay, we're going to condense this one. This is number 15. 6 times the natural log of x plus 5 minus 9 ln x. I'm doing it. So, I'm going to write my ln. Here's my ln. The first question I ask myself, do I need a fraction bar? And the answer is yes, because of the... Okay, right there. I'm deliberately not making it in red, so...
Until after
I've asked the question, okay?
Now, what goes on top?
What goes on top? X plus 5. Anything else up there? The exponent 6. Good. On bottom, x to the 9th. I agree.
ln. Okay, so I type ln, and it bolds it, so I've typed it correctly. Put the fraction bar.
And you have to have that x plus 5 in the parentheses because it all needs to be raised to the 6th power.
Come down to the bottom and write x raised to the 9th. Y'all caught up with us? Oh. Okay. Oh, I like this one. I like this one a lot.
Mm-hmm. You know something? I think, well, they're writing it down, so I'm going to write it down.
This is one of those
Four.
a common mistake people make on this one.
Mm-hmm. LNC. Okay. We're condensing the logarithms, so the 3 logarithms we're going to write as 1 logarithm. I'll write my ln.
Do we have a fraction bar?
Yes, because of the, okay, that minus right there is the thing that says we're going to have a fraction bar.
Now just be careful, but call it out. For the top, we put a x to the 4th, and what does he write next? Okay, y to the 5th. I was so afraid y'all were going to say plus. No.
Those pluses do not get transferred.
Well, if it did, it's a red dot, which you can't type in. I think if you start typing in the dots, they might, I don't know if they'll take it or not.
Okay. What have we got on the bottom?
What else?
Z exponent square.
So, common mistake is to put a plus right there.
This is back when they had all this multiple choice stuff. Here's one of the responses.
Yeah. Used to be, you look back at Pierce.
And in the homework, that's okay. If you chose the wrong response, okay, do it again. But on the test, you couldn't. And they'd have that, the programmers would have that sitting there, and people would choose it, and I just want to go and shake them. You cannot put that plus sign there. The plus does not transfer. The only way you can have a plus in your argument of the final answer is if you started with the plus in the argument of the original problem. Do y'all understand what I'm saying? We had an x plus 5. We've got to have an x plus 5 down here in the final answer. We had a z plus 3. We had to have a z plus 3. But you can't start off with something that doesn't have. There's no plus or minus in the arguments right there. So you can't have a plus or minus in the argument of the final answer.
Type that in. ln. But when as you're going through all of these, at this point, so often I have students ask me, well, do I have to show work or something? You know, well, no, if you can do it without x to the 5th. Oh, wait. Oh, I'm punching in all the wrong stuff. X to the 4th. Right arrow. Y to the 5th. Move into the bottom. Put a z squared. Okay, we're through expanding and condensing. What we're about to do on number 17, we're going to use a calculator with a logarithm key. And if I have not insulted your intelligence yet this semester, I'm about to. Okay? How do I punch in log 80? Well, I hit LOG. I put an 80. Now, this is a little tricky on my calculator and on most calculators, when you hit log, if it opens parentheses, get into the habit of closing them.
Here in this one problem, you'd be okay, at least with this model.
There's some of the
I
higher
remember
end
the
calculators.
TI-92 would give a programming error. Oh.
Yeah.
So, but and the next time we're going to be punching in some very messy logarithms. If you're not closing the parentheses whenever they open it, your calculator will open the parentheses, you type in the number, then close the parentheses. Mm-hmm. Otherwise, you're going to get some very wrong answers. They want it rounded to 4 decimal places.
1, 2, 3, 4. So that 30, am I going to leave it as 30 or should I make that a 31? 31. You look at the digit after 0, and if it's 5 or bigger, round it up.
With the usual rules of rounding.
1.9031. Now that's log base 10. That's the key that's on my calculator.
And let's think about what they're saying. 10 to what power gives you an 80? The log of 80. That's saying 10 to what power equals 80? Well, 10 to the first power is 10. 10 squared is what?
100.
100. So you've skipped past 80. But the answer has to be between 1 and 2.
And it is.
And
it
sure.
is. Oh, wait. I don't have to show that. Oh, wait. If I do that, 1.903 rounding to 1. So 10 to the 1.9031 power would give you 80. Wow. Okay. But on our calculators, the only keys that I have on this calculator is log, which is log base 10, and ln, which is log base 2.71828182885.
Suppose you want to evaluate a logarithm, and it's not a log base 10, it's not a common log, it's not a natural log. What are you going to do?
Well,
your calculator only has log and ln. Let's look at there, log base 3. Do you all agree we can't just figure this out on our own? 3 to what power equals 15? That's what number 18 is asking us.
What exponent goes on 3 to give you 15? See, this is one of those where we can't write it with 3 to a power. And I said, well, we'll get to that eventually, and that's what we are.
Log base 3 of 15. You're asking yourself. Here's what you're asking. There's a formula we'll use, okay? But you're asking yourself, 3 to what power? 3 to what power equals 15? That's what you're asking. You're thinking, well, 3 to the first is 3. 3 squared is what?
9.
3 cubed is 27. Well, 15 is between 9 and 27, so this answer has to be between 2 and 3. Did y'all follow my logic?
2 point something.
2 point something. But that's all we can do. We can't figure it out any more precise just thinking our way through it. We have the change of base formula. It takes logarithms like this and it converts them to either log or ln. I remember this being important in I remember our chemistry classes. Tony and I were always the last people that finished those experiments, okay? But at the very last lab in the second chemistry class, okay, that we were taking, the calculations required the use of logarithms and the change of base formula, and no one else knew the change of base formula. And the lab assistant.
You're reminiscing about something that happened
in 1984, 39 years ago.
Okay, that's what I was thinking. Okay.
Yeah, okay, but
anyway,
still. So this is important for other classes, okay? The change of base formula.
It's not a
hard formula. Let's say you have log base b of x. Log base b. You can convert it to any logarithm you want to using a quotient But for our purposes, if we're going to use a calculator, we're going to want it either in log or ln. So I'm going to state it only in terms of log and ln. If you're using ln, that's what I prefer. It's the natural log of the old argument divided by the natural log of the old base. Or, if you're...
you can do either one.
Or, okay. Or, you could use log.
Or whatever calculator key you have on your calculator. If you had some rare calculator that has a log base 2 key,
you could use log base 2 above and below. But most calculators only have ln and log.
I remember my nephew years ago, this just stands out. He was at a university and he was, I was being nosy. What are you doing in your algebra class? Logarithms. We just did change of base today. And I said, oh, so it's log over log. Which one goes on top? And he was like, X and B on the bottom. I said, how do you remember that? And he was like, well, I just remember it. Well, it's the one that goes on the bottom is the number that's written lower. Little subscript is the thing that goes on the bottom.
So let's look at that number 18. What do y'all like better, ln or log?
Which one do you want him to use? It doesn't matter as long as you don't mix them.
ln, that's what I like. You take the natural log of the old argument 15 divided by the natural log of the old base 3, ln 3. So ln 15,
watch out.
When you punch in that 15, what are you going to have to do before you continue? Close the parentheses.
So go ahead and put parentheses down here around these.
I'm going to. That's a good idea.
If your calculator opens parentheses, you make sure you're closing them.
Then divided by ln 3, close the parentheses, equals.
No. As long as you don't mix them, it doesn't matter if you used ln or log. But don't do ln for one of them and log on the other one. No, you'll get it wrong. But you see, I did ln over ln or log over log. Either way, you're still getting the same answer.
How do they want it rounded? That's why I didn't write it down.
Round to 4 decimal places.
So it's switch back for me to write up my answer. 2 point. Remember we said it had to be between 2 and 3, and it sure is. It's 2.46. Is that going to stay at 49 or is it going to go up to 50? They want 4 decimal places. It's going to go up to 50 because of that 7. So
this is
2.4650.
Don't do a lot of decimal numbers in this class, do
you?
2.4650.
Mm-hmm.
Okay. Here's another one.
Okay.
I won't use both log and ln this time. I'll just use one of them, I guess ln.
We should have made a point to illustrate that those parentheses are required. If they don't close the parentheses, then they're going to get the wrong answer. So, log base 2 of 0.20.
So you're going to write it as log over log, or ln over ln.
Right. I'll write a fraction bar. I have ln on top and ln on bottom. What's up here on top? Okay, the 0.2. On the bottom, then we have just the 2. Suppose you didn't close the... Well, let's first of all get the correct answer.
0.20, close parentheses, divided by ln 2, close parentheses. The reason we prefer for something like this to use ln is there are some calculators that don't have log keys.
The common logarithm is not that common anymore. Is it going to stay at 19 or go up to 20? It's a 3-2. Is it going to stay 1-9 or go up to 2-0? Is it? What's after that?
After the 9 is a 2.
I think it's going to stay a 1, 9. You're looking at the 8. You look too far, I think.
1, 2, 3,
4.
Hey, are we sure it said to round to the...
You better check. Sometimes they change it.
It's in the next assignment. For one time, you'll be rounding to 3 digits. Then the next problem, round to 4 digits and stuff. So,
okay.
So since the number after the 19 was a 2, that's
it's
smaller
a 1,
than
9,
5,
2. So we just drop it. And there's what they want.
Negative
2.3219.
Negative 2.3219.
Okay. Punch it in without closing
Oh,
the
yeah, that's what I
parentheses.
wanted to do. ln 0.2.
No.
Oh, where'd I get a 1?
I don't know.
ln 0.20 divided by ln 2. If I don't close those parentheses.
Am I going to get that correct answer? Let's see. Nope.
No. Okay. So watch out. This is going to be especially true in the first 3 problems of the next assignment. You've got to make sure you're closing those parentheses if your calculator opens the parentheses.
And I want to remind y'all of, okay, I want to remind
Problem
y'all,
number 20.
where is it? I want to remind y'all of these 2 statements we had here that say that the logarithmic to the base b and the exponential to the base b are inverse functions, and when they're performed consecutively, they cancel each other out. Now, I want to restate those for in terms of log base e, in terms of ln. I'm going to restate these 2 statements. Instead of an log base b, it's just ln. Now, what's the base of the ln notation? I don't see a subscript. It's an e to the x equals x.
So ln and e cancel each other out when they're side by side. Or write it the other way.
Okay, e to the ln x. As long as they're performed consecutively in either order, they cancel themselves out, leaving you wherever you started.
Jim, I'm afraid that looks like a 1 there.
You're right. That's just a squiggly there, separating the 2. Maybe I should write it here. I'll write it like that. E to the ln x equals x.
ln and e, when they're side by side with nothing between them, I'll write e to the ln. Okay. Now,
So with that in mind,
problem 20 looks hard, but it isn't.
we're going to use a logarithmic function. They give us the natural logarithm as a function. This is number 20.
F of x equals ln x. It seems like, oh, this is going to be hard, but no, it really isn't.
No, it ain't going to be hard. They want us to find 3 things. I'm going to write down all 3 parts. F of
E squared.
E squared. F of, hold on. F of and
E to the ln 6.
E to the ln 6. And E to the 5 ln 6.
Oh, wow, this is such a good problem.
I know.
Well, it requires that y'all remember something. With function notation, whatever's in the parentheses, you plug in for x. Draw the little arrow.
Oh, yeah, I've got to draw the
universal arrow.
Universal arrow of yours. Is that it there?
Uh-huh.
So this says, go to your function f, and wherever you see a variable, plug in what's in the parentheses. So we're going to plug in the e square in place of that x. So we're going to have an ln e square. What's that going to reduce to? If you perform ln and e consecutively in either order, what happens? They cancel out. So in this case, they cancel out, leaving us with 2. Okay.
E and ln cancel each other out when they're side by side. Let's just go ahead and do all 3 of these, then I'll punch in the answer.
The next one, we go up here, we replace the x with e to the ln 6.
Now, this one's sort of interesting because it's up to you how you cancel. Look at how these marks I'm making here. You could cancel like that, cover those
It'd
up.
be up.
So you just have an ln 6 as the answer. Or you can cancel the blue E and the blue ln, and you'd still be left with the ln and a 6. So it's just a matter of how you want to cancel. How do you want to mark it out?
But it's not a cancellation free-for-all. Some people get into their head that if there's an E and ln in both and if they're both in the same problem, they all just disappear and leave you with just a 6. I know that's what they're trying to get at here with this problem. It doesn't just all disappear. It's a one-to-one correspondence. You can cancel out one E and one ln. Well, either way, you're going to be left with an ln. For the final answer, ln 6. But it's not just a cancellation free-for-all where every e and ln just disappears. They've got to be consecutive, and it's just a pair.
Now, for the last
one, ln.
On the last one, you don't have a choice on which to cancel. There's only one way you can mark out and cancel. The E and ln have to be side by side with nothing in between.
Can I cancel the blue E with the blue ln?
No, because there's a blue 5 in between them.
All you can cancel, that one pair right there. So your final answer turns out to be
5 ln
6. I guess you can move the 5 up on the 6 as an exponent and get ln 6 to the 5th power. But then
216 times 36, I can't do that in my head.
So why bother? Just leave it as 5 ln 6. What they're trying to make the point of with these problems is that true, E and ln are inverse function, but they don't just magically disappear. It's a one-to-one correspondence, and they've got to be consecutive.
No, there's no way you could cancel this E, the blue E and the blue ln, and wind up with an ln 56 or something. No. So let me type those answers in. 2. Okay.
ln 6.
ln 6. Remember, it's ln and not a in. And what was this one? A 5
ln 6.
ln 6. Okay. Any questions over all of this? I know it was a lot, but it's really not that bad. Once you get the hang, the majority is what? Condensing and expanding. Once you get the hang of that, then these other little things are.
And I know this is bad, but your class will be easier on Monday if you've already gone through this homework before Monday.
Yes, we have one more assignment with logarithms. Oh wait, I'm already through here, so I'm going to go ahead and stop recording. Are there any questions? Stopping recording.